Hey everybody, this is Johannes from Xyna. Today we learn how to model concurrency with Xyna. And as always, we use our vehicle setting for this. Imagine there is a gas station with some petrol pumps of different kind. Since there is a limited number of petrol pumps and each vehicle occupies one pump while being refueled, we need a mechanism to queue vehicles waiting for fuel. First of all, we build a workflow to refuel one vehicle. We use a type choice to choose the right petrol pump depending on its drive type. Now to the first mechanism to manage concurrency in Xyna: capacities. In the factory manager there is an entry for them. A capacity sets a limit on how much workflows may run in parallel. The cardinality says that this number of associated workflows can run in parallel at a max. We create one capacity for each petrol pump kind with a cardinality for the amount of petrol pumps of this kind. We have two diesel pumps, for example. To associate a workflow with a capacity, go to the workflow's order type and scroll down. There is a list of all capacities. You can associate a workflow with multiple capacities and vice versa. In our case, we associate one workflow with one capacity. For a test, let's start some refuelings for different drive types. To watch the current occupancy of capacities, there's the capacity monitor. On the top layer, you see one line per capacity, including its current occupancy. On the right, there's a list of the running orders IDs. If you open the details, you also see the order status, order type and usage. A more interesting case is to have more orders than the capacity allows. In the header field, we see that the capacity is fully occupied. We also see that there are two other orders waiting for some free space inside the capacity. These are the orders exceeding the capacity's cardinality. As soon as one running order has finished, one of the waiting orders moves up. Another mechanism to control concurrency is a veto. To explain them, imagine you're at IKEA's with your kids and need the baby care room to change a diaper. There's only one room, so you need to control the occupancy for this specific unique instance. This is what vetoes are for. Vetoes associate with unique items and workflows accessing this item. In the IT, a usual case would be write access to a file. Vetoes are defined a bit differently than capacities, although they have very much in common. To set a veto for a workflow, you need an extra planning workflow for it. Each workflow has a default planning workflow to plan its execution in the scheduler. The planning workflow is automatically executed before your actual workflow gets executed. To occupy a veto with your workflow, create a planning workflow for it. Use exactly this service to get the corresponding scheduler information. This scheduler information has an empty list of vetoes, which you could fill with veto names. Arbitrary but unique names. As soon as your workflow starts, these vetoes are occupied and no other workflow trying to occupy one of the veto names can be executed. As soon as the workflow finishes, the veto is deleted and workflows waiting for this veto start automatically. There is no constraint on how to name your planning workflows. It's common practice though to name it like the destination workflow with planning as prefix or suffix. Now let's connect the planning workflow with our diaper workflow. At the moment, these two workflows are not associated with each other. We again control this via the order types. The first entry tells us which planning workflow is used. As I said, a default planning workflow is used by default, without setting any vetoes. We want to use our special planning workflow to set the baby care room veto. Don't forget to save your changes. When we now launch our diaper workflow multiple times, we expect that they will run only one at a time. Looking into the veto monitor confirms this. 2 orders are waiting for the veto to get free. There is also a link to the currently running order occupying this veto. After one order has finished, the next one occupies this veto. Yet another way to control concurrency is the await and notify service. This mechanism allows you to synchronize 2 concurrent workflows and even transport some data between them. Our example is as follows. We refuel our car and then start the payment process. But the payment process needs the actual amount of fuel we filled in our car. If our car is still being refueled, the payment has to wait. It has to await the actual amount of fuel. The await step will pause the workflow until it receives data from a correlated notify step. To identify the await, we use the vehicle's registration number. The output of the await shall contain the amount of fuel we have to pay for. On the other side of the process, we have to call the notify step and put in all information we are awaiting in the payment process. We again use the vehicle's registration number to correlate the notify with the await. Then we write the amount of fuel into the synchronization answer, which will be the output of the await. When we now start both workflows and watch them in the process monitor, we see that the payment workflow is paused at the await step, because the refuel workflow has not reached the notify step yet. As soon as the notify step has been executed, the await receives the amount of fuel to pay for and the payment process continues. There is one last mechanism to control concurrency for today. If you want a service step to run asynchronously, you can call it detached. Such a step has a small d attached on the right. Since the workflow continues its execution directly after invoking the detached step, the output of the refuel service cannot be used inside the further process of our workflow. If you enjoyed listening, don't stop and try this out on a free Xyna community instance. We also have a video how to get one. or watch some of our other videos about Xyna. Goodbye and thanks for watching.